selective repeat. This is the second big categories of the pipeline RDT. So its design is pretty much the opposite of go back N. So in go back N, you have cumulative act. So the sequence number in the act there is to indicate all the packets before these particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go back N, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. All right, so receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. And the reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrived at the receiver, 2 get lost, 3 arrived at the receiver. You cannot be just extracting the data bits out of packet 1, pass it up to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order at the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. And you wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the n-act packet. So what is the maximum sequence number there can be n-act. As opposed to in go back N, we say n being the number of n-act packets. Right. The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, all right, and after the yellow packets, the blue packets. In go back N, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. All right. So even though they're turned green, but that doesn't mean that, hey, we'll include these 4, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be an act, not the maximum number of packets can be an act. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. Right? And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The blank ones are just not possible. So if we receive packets after receive base plus end, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that. And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah, what I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. Yeah. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? Right? So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is a timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unACK packet, so if n here is also the smallest unACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the send base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next unACK packet. All right. So this is sender's actions depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range. The receive base and receive base plus n minus 1. So that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packet, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So that's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an egg for that packet back. If you recall, it could happen, right? The egg packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is going to fire it again and again and again, and the sender there is going to retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. So those that are outside, just ignore it, because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.